So we were discussing this very important problem from the book by Shamsher Prakash, Soil Dynamics book by Shamsher Prakash, and this example 9.1. Now, obviously, if you see the problem, so thing is that we have to take outs. We have to take parts of this example and understand the various steps. Uh, the second part which I have discussed, that is, which I have shown actually, I have not discussed that. That is basically finding out the center of gravity of the foundation block and the machine as a whole. Once you find out the center of gravity, then you find out what is the eccentricity, then you find out what is the moment of inertia of the base area, okay, polar moment of inertia, area moment of inertia about the y-axis, polar moment of inertia about the z-axis. Then you find out the mass moment of inertia about the y-axis passing through the CG, okay, center of gravity of the combined mass and foundation system. Then you find out the moment of inertia, mass moment of inertia about the axis passing through the point of rotation. That is a O point which we have shown that when there is a rocking and sliding motion combined, so there is a point about which the foundation rotates or moves. So about that point. So all that is basically geometrical and as far as the soil dynamics thing is concerned. Of course, if you are going to design that in the future, when you'll be a this consultant engineer or something like that, obviously you are going to use that. But thing is that that has nothing of a concept to understand or something like that. It is very a geometrical problem, and the thing is that you have to analyze it geometrically. So what we are going to do is we are going to lay emphasis on the soil properties basically. Okay, so the soil properties part. So the dynamic soil properties. That is actually the more important part. So if you look into the problem, you will see that there are various data given. First of all is the subsoil profile given. So this is the subsoil profile. Subsurface soil profile, that is. So in short we say subsoil profile. So basically it is given what is the type of soil, where is the groundwater table, okay, then what is the water content at various depths, and where it lies. So this is important, where it lies in between the Atterberg limits. So plastic limit and liquid limit. So you see that it is lying in between these two and it is closer to the liquid limit. Okay, so that is it is a serious condition. We should take note of that. All right, so the soil will behave somewhat plastic in nature. Okay, so its behavior will be somewhat plastic in nature. So that is an important part. In fact, here also, but thing is that this soil SM and SMSC, okay, so they will most likely or their behavior will be predominantly sandy or granular in nature. Okay, so their behavior will be sandy or granular in nature. So obviously these things are actually to be taken in the soil mechanics course, but I'm just giving a quick revision so that it becomes clear, right? So why it is necessary. So apart from that, we have the SPTN values. So you have definitely come across when you have studied foundation engineering. All right. So for design of foundation, so for analyzing the allowable bearing capacity or safe bearing capacity or net safe bearing capacity, so we can use the SPTN values. All right. So there are various correlations Of course, we have to use n corrected. Alright, and we can find out what is the SBC or what is the allowable bearing pressure. Okay, considering the settlement and considering the shear failure criteria. So shear failure criteria and settlement criteria. So you can look into that. So obviously this is the first and most important data for any soil geotechnical engineering design. Alright, so you go to design retaining wall, you go for designing of foundation, you go for designing of anything, alright, related to geotechnical. So subsoil profile is the first and foremost data. Now apart from that, if you look into the problem, so it is given that we have to determine the plot of coefficient of elastic uniform elastic compression. Okay, so coefficient of uniform elastic compression, we have to find out Cu versus the strain. So versus the strain, right? Vertical strain, that is. So vertical strain, whatever is the strain, at confining pressure of 1 kg per centimeter square. So that is what we have to find out. Okay, so this is an important part of the problem. So if you look into the problem, so you will see that there are various data given. First of all is the cyclic plate load test data given. Okay, cyclic plate load test data given. And we have already discussed how we obtain the data. So we basically have a plastic deformation. So suppose we have a total settlement here. Okay, so we have some amount of plastic deformation, the major amount of plastic deformation, and we have some amount of deformation which is recovered. So that is considered the elastic settlement. Okay, and that is plotted here, or I mean noted here. And after it is noted, we plot it, and ultimately we get the Cu. So basically the slope of this is the Cu. Obviously we will see that the Cu varies with the load and the deformation as well, all right, with strain. So we will see that afterwards. So that this is the first data given. Apart from that, you will note that so block vibration test. So basically vertical block vibration test has been done. So vertical block vibration test has been done. So you see this is the amplitude and this is the frequency at resonance. So at resonance, that means applied frequency is equal to natural frequency of the system. And obviously we have the maximum amplitude. So this is the amplitude recorded. So similarly we have, so here you see it is a little bit less than 1400 the frequency. So it is given 1360 rotations per minute. Okay, and amplitude is 0.15. Here the amplitude is this much. So amplitude varies with frequency. Okay, so amplitude varies with frequency. If you plot them all together, you will find that this plot is somewhat like this. Okay, then you will find this plot is like this. Then you will find this plot, and then you will find this plot. Sorry, this will be the lowest one. Okay, amplitude is the, no, this will be this one. Okay, like this. Okay, yes. So here you see frequency is decreasing. So here it is maximum, it is 1600. Okay, so here it is 1600. Then here it becomes approximately 1400. Okay, then here it becomes no, here it is more than 1400. Okay, so yeah, this first is this one, then second is this one, third is this one, and fourth is this one. Okay, so first, second, third, and fourth in this way. Okay, so this is the block vibration test, vertical block vibration test data given. Then apart from that, a surface walk propagation test was also done. Okay, surface wave propagation. So basically we have a dynamic load here, and what is the travel time, it is noted. Okay, and the frequency is given, frequency of a particular frequency is applied, and we have a particular wavelength, and we note the time. Okay, and we measure the shear wave velocity basically. Okay, so we measure the shear wave velocity. Now as we have seen before, so basically the effective depth, so the effective depth or the depth of this influence of this wave, okay, influence of this wave, it is basically L by 2. All right, so this is L by 2. So just recollect that, and we will come to that. Why is this so important? Okay, why is this so important? So this was given by Woods in 1978. All right, and it is empirically related to the L by 2 length. So yeah, so these are the data which are given. So we have to find out this one. So first of all, about analyzing the plate load test. Now if you remember, we have a plate. Okay, we have a plate and it is loaded. So thing is that we have to now find out what is Cu for a confining pressure of 1 kg per centimeter square, or pressure of 1 kg per centimeter square. Alright, so Cu corresponding to 1 kg per centimeter square, and for an area of loaded area of 10 meters square. Okay, so for 10 meter square area we have to find out. So this is what is asked in the problem. Now the plate load test which was done, it was done for a plate of 60 centimeter by 60 centimeter. Okay, so it is 0.36 meter square, but the area that we require is 10 meter square. Okay, so if we divide this by this, we will get Cu corresponding to load of P is equal to 5 ton per meter square. Okay, and the strain, vertical strain will be 0.7 mm by 600 mm. Okay, so just a second. Oh, sorry. Oh, sorry. Yes, yes. Oh, oh, sorry. Oh, sorry. Soil dynamics. Now, Malong, sir. Malong. Oh, Malong. Yes. So how to find out this strain? So if you remember, if we have a foundation, so with B, so when it is loaded, so there is a formation of an elastic wedge. Okay, so this was first proposed by Prandtl in 1920. So this elastic wedge. So initially it was thought that this is phi. Okay, then Terzaghi and then later Vesic. Terzaghi in 1943, so he used this concept and he formulated the famous bearing capacity equation. Okay, so the bearing capacity equation, of course you can still look into that. So we are concerned with this depth. So Vesic in 1973, so Vesic in 1973, so he said that this is not phi, so this is theta, where theta is equal to 45 degree plus phi by 2. Now if you note the angle of internal friction phi, for majority of the soils it falls around the range of 30 degree. Okay, so theta, it is approximately equal to 45 degree plus 15 degree, 30 by 2, 15 is equal to 60 degree. So basically this is an isosceles equilateral triangle or isosceles triangle. Okay, so this depth we can consider it to be beta. So there is an elastic wedge. So this is the elastic wedge. So depth is B. Okay, and we have to find out what is the stresses at the center of this depth. At the center of this depth. Okay, we have to find out the center of this depth, and we know that settlement is already given. The elastic settlement is 0.7 for 5 ton per meter square, then 0.8 for 8 ton per meter square. Okay, 1.3 for 12 ton per meter square. Okay, so it is already given. So we can find out. So epsilon v we can easily find out now. So it will be the settlement, whatever is the settlement. So suppose it is, if we consider this 15.5, it is 2.25 mm by the width of the foundation. So width of the foundation, it is given 60 centimeter. Okay, this plate means the plate with which we did the plate load test. So that is divided by 600 mm. Very easy. So this is epsilon. So that is easy. Now thing is that when we load an area with a stress QS, so the stress is distributed throughout the soil and it is not same with depth. So with depth, basically the stresses gets distributed, so it gets reduced. Okay, so we have to find out what is the stress at this center, that is B by 2 at this center. So that means we have to find out, so if it is 60 centimeter, we have to find out that 60 by 2, sorry, is equal to 30 centimeter. So that means 0.3 meter. So we take help of the Boseniuk's formulation. Alright, so if you remember Boseniuk's, so he gave the first solution for the point load on the surface in 1885. Okay, so he gave the solution for a point load. Then it was extended by Taylor in 1948. Okay, then by Giraud in 1968. Okay, so various researchers over the time has given various ways to find out the elastic stress. Okay, I mean the stress at a particular depth considering elastic settlement of the soil. Okay, so the soil is considered elastic material while analyzing this stresses. So now we have to find out at a depth z, that is 0.3 mm, sorry, 0.3 meter, what is the stress. So what it is done is, the plate was, if you remember, it was 60 centimeter by 60 centimeter. So it is divided into 4 and we take only one part. So it is divided into 4 and we take only one part. So the rest we for a while forget. So the length of these sides are all 0.3 meter. Okay, length of these sides are all 0.3 meter. So now m factor here. So m is given by b by z. So z is 0.3, b is 0.3. So m is equal to 1. Similarly, n is equal to length by z. Okay, so length is also 0.3, z is also 0.3, so n is equal to 1. So now we have to obtain the increase in the stress at the depth of 0.3 meter from the base of the plate. What is the increase in the stress? Delta sigma z. So that is given by Iz, which is the influence factor, into the Qs, which is the stress applied here. Okay, so Iz is, so here it is n is equal to 1. So n is equal to 1 and m is equal to 1. So m is equal to 1. So this is the intersection point. So Iz is equal to 0.18. Okay, so this I am just doing to recollect the things. Alright, so delta z is equal to now 0.18, or in the book, in the example, it is given 177, almost same. Okay, so into we have the stress which is applied. That is, in this case, it is considering 15 ton per meter square. 15 ton per meter square. Okay. Now what is, now this is delta sigma z. Okay, so this is increment. So obviously we have taken only 1/4. So we have to multiply that into 4. Okay, so that is the increment in delta z. Now obviously we already have some initial pressure there, right, due to the soil, weight of the soil. So that will be sigma zi initial. So that will be unit weight of the soil. So it is given 1.8 ton per meter square, meter cube, sorry, 1.8 ton per meter cube it is given. So into that depth, that is into this depth, that is into 0.3. So ultimately total pressure now at this depth z, sigma z is equal to sigma zi plus delta sigma z. Okay, so following this problem, following this method, all right, so following this method, so I have obtained the load at the depth of 0.3 for all of these load areas. All right, load, I mean plate loads which was given. All right, so this was given on the surface at the depth of 0.03. Whatever is the stress sigma V I have calculated using this procedure. So here in case of 15, it will be either this one or this one or this one, whichever you place. Okay, so sigma Zi will remain same. So basically, if I just delete this, so sigma Zi, it will remain same 1.8 into 0.3 ton per meter square. Okay, so this is meter 1 ton per meter cube, and this is meter square. Now delta sigma Z will be same here 0.18, it will be same. So 4 into 0.18 into, in this case it will be 5, in this case it will be 8, then in this case it will be 12, then in this case it will be 15.5, okay, in this case it will be 19.5. So that will be delta sigma Z. So correspondingly you will find out the CU. So CU is basically this divided by this, CU, easy, okay, corresponding CU. Now the thing is that this is CU1, okay, we need CU2 for stress of 1 kg per centimeter square, okay, sigma V should be is equal to 1 kg per centimeter square, and area A should be equal to 10 meter square. So you remember this, so we need CU2. So CU1 is these values. So 5 by 5 ton per meter square by 0.7 mm. Then 8 ton per meter square by this one. What? This one 0.8 mm. Okay, these are all CU1. So corresponding CU2 will be given by, so we know that CU2 is equal to, by CU1 is equal to E1, E2 by E1, G2 by G1. So remember this expression, it is very handy expression, alright? And we have, in case of stresses, we have sigma 2 by sigma 1, and area we have A1 by A2. Okay, so just put, so A1 will be 0.36 meter square, which we have found out here, alright, so 0.36 meter square, and A2 will be 10 meter square, which is required. Okay, and sigma 2 is this one, so plus sigma 0, so sigma 2 will be from here, and sigma 1, sorry, sigma 1 will be this one, this plus this is sigma 1, okay, for various loading conditions, and sigma 2 will be 1 kg per centimeter square, so that is sigma 2. So we will have Cu2 for various loading conditions. So in the book it is given for only 15 ton per meter square, and the settlement was, elastic settlement was given to be 2 mm. So the corresponding Cu1 was obtained as 1.36 kg per centimeter cube. Sorry, this is Cu2. Okay, Cu1 was found out to be 7.6 kg per centimeter cube. This is Cu1, okay, and Cu2 is ultimately we found out. So Cu2 we found out to be equal to 1.36 kg per centimeter cube. Now this is given in the example problem. So apart from that, I also calculated for this other values and I plotted the data. So this is the thing. Okay. Yeah. So apart from that, and I plotted the data. Of course, we are coming to that. So apart from that, the block vibration test was given. So a block of this is 1.5 meter as given in the IS code. Then the width is 0.75 meter, and this is 0.7 meter. So IS code specification. Okay, and so here, from here, from this data, okay, so the CU corresponding to that was obtained. So that is obviously very easy. So direct formulation you can find out. So Cu is equal to 4 pi square Fn Z, right, into mass, combined mass of the this foundation and the machine, right. The machine you can take to be 100 kg. So divided by A, that is the area of the base of the foundation, which is 1.5 into 0.75, right, in meter. Of course you have to take units, has to be consistent, units has to be consistent. Okay. So similarly, here also we have the stresses, different stresses. So this is the area and the stresses are different. So corresponding to that, we have the Cu dash corrected for the area. Okay. And then we have the Cu dash corrected for the pressure. All right. And this is the amplitude, the maximum amplitude, Az. So Az, it is already, I mean, it is already here only given. So Az is given here. So that is the maximum amplitude. So from the maximum amplitude, we have plotted the strain. What is the maximum strain? Okay. And to find out the strain, so it is Az by, so Az is the maximum amplitude by, so here you see it is 0.75 mm, I mean meter is the width of the foundation, B of the foundation. So that is 750 mm. Okay, that is the width of the foundation, A is equal to B. So Az by B. Alright, so that is strain. Alright, so we have found out the strain. So these are the strain values given here. So for converting the Cu to Cu dash to Cu double dash, same thing. So this is for area correction. So root over A1 by A2. Alright, so that is corrected here. And this is for the pressure correction. So sigma 2 by sigma 1. So that is the pressure correction, nothing else. Alright, so same as we have done here in this case, just in case of the plate load. Okay, so they have obtained the Cu dash, which will be required for the design. So this is the Cu dash corrected for the stresses, vertical stresses and the area, and this is the strain. All right. Now these are all at the higher range of strain. All right, so higher range of strain. These values Cu obtained from these values, the cyclic plate load test. All right, cyclic plate load test, as well as the vertical block vibration test. So these are all for higher range of strains. All right, so high strains. Now to obtain at very low strain, all right, so strain here, when there is a wave propagation being done. So the strain is approximated to be, vertical strain is approximated to be 10 to the power minus 6 meter, in the range of 10 to the power minus 6 meter. Okay, so this is of course thumb rule, all right, standardized thumb rule for wave propagation, test. Okay, so this surface wave propagation test was done. Okay, and it was found out that the shear wave velocity is 314 meter per second. Okay, 314 per meter per second. So we obviously know that G max is equal to Vs is equal to Vs is equal to root over G max by density of the soil, right, or unit weight of the soil basically. Okay, unit weight of the soil. So from here you can find out, this is density, not unit weight, sorry, it should be density, not unit mass. All right, so it has to correlate with mass, not weight. So mass is density and weight is unit weight of light. So here it is unit weight. Okay, so ultimately we put this value here at this place. So we have G max is equal to Vs square into density. So that is G max. Okay. Then to find out Cu, so what we do is, so Cu is equal to, it is given 1.3 into, we have this formula derived for the finding out the elastic coefficients from the block vibration test. So 1.3 by 1 minus 1 minus mu square, alright, root over A, that is area of the foundation. So here E is the elasticity coefficient of elasticity, and mu is the Poisson's ratio. So mu you can take to be 0.3. Okay, so in no volume change case, so 0.3 you can take mu. Area is, you can take the area given to be 10 meter square, which we want to find out. All right, and E, now we have to find out E. So finding out E, definitely we can find out E from the G value. So we know that E is equal to twice of G 1 plus mu. Okay, so you can find out E from here, G. So you put it there and you will get Cu. Now this Cu is for this effective depth. Alright, and the stress condition is what is at this center. Okay. So the wavelength, lambda L or L, whatever you say. So for our wave, it was given that given by Woods 1978, that this is, we can approximately take to be equal to 12 meter. Okay, so we can take to be approximately equal to 12 meter. Now if this is 12 meter, if this is 12 meter, length of wave is 12 meter, then the effective depth, or depth of I mean this influence of the wave, all right, so that is 12 by 2, that is 6 meter. So this is 6 meter. Now what is the stress here at this point? So that is at this 3 meter. All right, so that we can take as mean stress. Okay, so sigma v. So the mean stress for here, we will take sigma z is equal to 1.8 into 3. So that is the mean stress here. Now we want our Cu. Now Cu, which we found out from this expression now here. All right, putting Gmax. So Gmax we have found out from Vr square into density. So we have put it here. Then from there we found out E. From E we put it E here. All right, and then we found out what is Cu. Now that Cu is correlating to, I mean corresponding to this amount of sigma z. Okay, so again we have to apply this equation. So this equation here to find out what is the corrected Cu in that case. Okay, so in that case Cu will be, so here 1.8 into 3, it will be 5.4 ton per meter square. So it will be 5.4 ton per meter square. So sigma z is given by 5.4 ton per meter square. So that is what is Cu correlated to. So we want it for 1 kg per centimeter square. Okay, we want it for 1 kg per centimeter square. So you just put it there in the expression and you find out what is the Cu dash. Okay, for 1 kg per centimeter square. So ultimately, we will get the Cu value. So this is the Cu value corresponding to, so these are all Cu values corrected for pressure of 1 kg per centimeter square, or stress of 1 kg per centimeter square, and area of, so sigma z is equal to 1 kg per centimeter and area is equal to 10 meter square. Okay, from the this data which was given. Okay, and these are the strain levels. So strain levels already it has been calculated here, it is shown. So how to calculate the strain levels here? So this is Az by B, so that is plotted there, and here from the plate load test it is obtained. Okay, and here we consider to be 10 to the power minus 6. All right, so EV we consider to be 10 to the power minus 6. So we plot it. First of all, we plot this point, this 2 here. So 10 to the power minus 6 and 25 kg per centimeter cube, or ton per meter cube actually. All right, so ton per meter cube. So correction there. Okay, so that is first point. Then obviously the other points. So other points are also plotted. Now here in the example, it is given 1, 2, 3, 4, 5, 6 points. So 1, 2, 3, 4, 5, 6 points are plotted. So what I did was here in the plate load test also you can see there are other points. Okay, so in the plate load test it was given 15 ton per meter square, and corresponding we have 2 mm of settlement. Okay, corresponding to that, CU was obtained and CU was corrected for area and stress. Now I obtained it for the other values as well. Okay, and I plotted it with the values given in the book, and it correlates well. Right? So you can see this. So this is what I have plotted. So this is from the book. Okay, then apart from that, we have this from the book, from the block vibration test, that is block vibration test 2.59, 2.59. Then this is from calculation. Okay, 2 point, so this is 75, this is 75. Alright, so correction here. So this is 2.75, then 2.97 and 3.6. So these are from the book. Apart from that, we have 1.36. So 1.36, actually this is 1.36. Okay, so 1.37, same thing. So this is from the book. So other points I obtained and plotted. So you can see this orange dots. Orange dots are actually from the data from the book. Okay, and cross is what I have plotted. Right, and they correlate well. And I could find out the curve. So y is equal to this one. This is the function of the curve, this curve. Okay, this is the function of the curve. So this is a power curve. So you can place this curve here, and you can get this constants. All right, so this is a power curve, and obviously it correlates well. All right, so r square is almost equal to 1, so 0.991, so it is almost equal to, so very good correlation is there. Okay, so you can try that out. Now you can find out any value of Cu corresponding to a stress of 1 kg per centimeter square, okay, and area of 10 meters square, corresponding to whatever is your amplitude of motion. Now if my amplitude of motion is suppose 10 to the power minus 4, then I will take 5 into 10 to the power 3 ton per meter cube, or 5 kg per centimeter cube. Okay, so that I can take from here. Okay, so that is the solution. So this is the solution of the problem. I just want you to go through that. Okay, understand that problem and look into that, because this is very important problem as far as dynamic soil properties are concerned. Apart from that, so here, yeah, so here you see, obviously, so with dynamic strain, so stiffness decreases. All right, so soil stiffness decreases. So obviously Cu will also decrease. So what, this is what we found out here. Okay, so Cu value, so this is for the shear modulus G, shear modulus, so we have this decrement in the shear modulus, and this is for the Cu, decrease in the Cu. Okay, so in our case we got somewhat in of this manner. Alright, so you can see free vibration test. So these are all free vibration tests. Alright, and we have the cyclic plate load test somewhere here. Okay, in this range, and we have the laboratory test in this range. Cyclic plate load shear modulus test. Okay, and shear modulus test we have here in this range. Okay, so various ranges and various tests. Alright, so different tests, different range of strains. and therefore different stiffness which ultimately leads to different coefficient of uniform elastic compression. Okay, so the second part is obviously we have to find out what is the CG. Alright, so if this is a cube, so definitely it will be at the center, here at the center. Okay, so we have the CG here, one CG here, then we have the one CG here. Okay, then we have the other CG here. So if these are the three CGs, so we can find out, so finding out the moments about this axis or whichever axis you require. Alright, so you find out the moments about the CG and you find out what is the combined CG of the entire mass. Alright, either in the y-axis or the x-axis, either some of the axis you consider. So that I think you can do. Okay, I'm not going into detail of that. So that is how you find out the CG of the system. So here you see, so the weights of the dimensions of the elements are found out, weights of the elements are found out. Okay, and these are the coordinates of the CGs, and these are the static moments. Right, so static moments about that CGs. Now in the third part of the problem, so that is one important concept given here. So if you look into the third part of the problem, you will see that it is given the exciting force is generated by moving parts and it is given as Pz is equal to 3 sine twice pi into 10 into that is this one. Okay, so twice pi into 10. And it is given there are two cylinders. Okay, there are two cylinders basically. So there are two cylinders which move out of phase. So this is an important part. So move out of phase by pi by 2 or 90 degree, that is. So that means what? So if I have a mass, suppose, so we have two mass. So one is hanging by the spring M, one is hanging by another spring M. Move out of phase means when this mass is at its maximum displacement, this mass is at its zero position. When this mass comes down to its maximum position, now this mass, it moves up to its original position. Okay, now when it will go up, this will go up. So now when this mass is back on its original position, this mass will be now here on top. Okay, so I hope you could get the motion of the two masses. So they move out of phase by 90 degree. Okay, so how to get the resultant force? So to get the resultant force, what we do is simple factor summation. Alright, so in fact this you have been continuously doing it. This is another way of putting it. Alright, so here what we do, so total force we consider it to be Pz, which will be equal to, first of all, the movement of the first mass. Okay, so that will be Pz1 sine of omega t. Now if this is omega t, this mass is moving at a phase difference of pi by 2, and therefore it will be plus Pz2 sine omega t plus pi by 2. So this is the phase diagram. So we have the force 1, so this is force 1. Okay, so this is already, some time has passed, so that you do not worry about this one. Okay, so some time has passed, that is why this omega t, that is. Okay, so this is sine omega t. Then Pz2 sine omega t plus pi by 2. So plus pi by 2 omega t plus pi by 2, we have this phase over here. Okay, and ultimately this force will, applied force, it will constantly rotate about this axis. Alright, and then whatever is the component of that on the y-axis, that will be the resultant applied force on the foundation. Okay, so that will be the resultant component force. Now what will be the phase here? So it will be omega t plus pi by 4. So this is pi by 4, this is pi by 4. Very easy. Okay, so ultimately the force, it will be Pz, total force. It will be moving at a, so it will be, suppose, a small Pz, here if I write the total force as small Pz, okay, small p z is equal to capital Pz, which is this magnitude, that is, into sine of omega t plus pi by 4. So pi by 4 is the initial phase of the total applied force on the foundation. Okay, and what is the magnitude of this force? Maximum magnitude. So obviously it is root over Pz1 square plus Pz2 square. So here you can find out. So if this is Pz1, this is Pz2. So a square plus b square, root over a square plus b square. Easy as that. Okay. So amplitude of this is given 3. Alright, so both of the, applied forces, dynamic forces, the magnitude is 3, I think, whatever unit it is given. Alright, so you check the unit. So it is given 3 units. So definitely 3 square, 3 square, it will be 3 root 2. Alright, PZ. So 3 root 2 will be the PZ. So very, very easy. Now, thing is that it is acting at an eccentricity. So you can see it is acting at an eccentricity. So now definitely there will be a movement. So how to find that out? Now we cannot directly say it is Pz into L, alright, because this will be pulling up, this will be pulling down, then again it will be pulling down, it will be pulling up. So there will be an this nullifying factor of the two forces. Okay, so we have to consider that. So how to consider that? So to do that, what you do is, so let us consider this is the CG of these two systems. So this is the axis to the CG of the two system, which is at a distance L. Okay, so this force it is acting at a distance of L plus LC by 2. So LC is the center to center distance of the two forces. Okay, so this force is acting at the LC by 2, whereas this force it is acting at a distance of L minus LC by 2. Okay, so what is the total moment now? Very easy to find out. So ultimately My is equal to, so Pz1 sine of omega t. So this is the force into the lever arm. So into the lever arm, L minus LC by 2. So force into lever arm. Alright, force into lever arm. So plus, so this is one moment. What is the other moment? So we have plus again Pz2 sine of omega t plus pi by 2. Okay, so this is the force which is at a phase difference of pi by 2 and into the lever arm, L plus LC by 2. Okay, so ultimately if you see here, so the moment from this force, so this is 3 and this is L minus LC by 2. Okay, so some units of L and LC by 2 are given, so you find that out in the text. Okay, so that is up to you. So if L is here, so L minus LC, so definitely it will be reduced. Okay, so the moment will be reduced. So this is the reduced moment, right? And its magnitude is 0.9. It is given here. So 3 into L minus LC by 2. So that is this moment. Okay, so 0.9. The other one is 3 into L plus LC by 2, which is 4.5. Okay, and obviously it is also at a phase difference of pi by 2. Alright, so this is pi by 2. But here you see, obviously the moment my, now you can find out maximum magnitude of the moment. It is equal to root over 0.9 square plus 4.5 square, that you can find out. Okay, and phi, the phase difference, will be y by x, tan inverse of y by x. So tan inverse of 4.5 by 0.9. Okay, so that is a phase difference phi. Okay, so I hope this concept is clear with you. So now, as we have already discussed in the previous slides, in the previous classes, you have to find out what is the, this basically the amplitudes. All right, so Az, amplitude in the z direction. Then you have to find out what is angular rotation about the y. All right, maximum angular rotation. Then you have to find out what is the amplitude along the x-axis. Okay, similarly you have to also find out, so here it is only given in the x-axis, so you can find out x-axis, no problem. If the problem is in the y-axis also, you have to find out in the y-axis as well. Okay, so these things you have to find out, and you have to limit that. Okay, limit that. Apart from that, you have to find out the natural frequencies as well. So omega n tx, omega n tz, omega n phi. Okay, this you have to find out, and you have to make sure that these are not matching the operating frequency of the system, which is omega. So not a very complicated problem. Only thing is that it is very tedious and time consuming, and that is the the real problem it is, because you have to do a lot of trial and error. Okay, the important part is understanding how to find out the soil parameters, okay, and how to use that. So look into the problems in try to understand that. Okay, it is a very good problem, that is why I'm telling, not from exam point of view, but as a learning process. Okay, as a learning process, it is very important problem. So we have discussed regarding the dynamic response and dynamic analysis, and how we can the various aspects that we need to take into consideration while designing the machine foundation, and we need to see and look into those aspects like the frequency, the amplitude, the force. Okay, so various aspects. So, and how the the foundation and the soil and the machine, and they will interact with the the foundation soil as well as with each other. Okay, so that is for reciprocating machines. Now we move on to the other type of machine, which is the impact type. So as at the start of the discussion, I have told you that in impact type, what it is done is, so there is a hammer, and that hammer is dropped. So there is something to be hammered down here, right? Something to be hammered down, and that hammer is dropped, and whatever it is thing is there, it is hammered in a way. So thing is that suddenly there is a load. Okay, so there is a load here. Now that load is taken up by two systems. One is a pad here. Actually, it is shown here, so we can consider this to be the pad. Alright, so one shock absorbing system. Okay, and then of course, obviously, we have the foundation at the bottom. So what we do is we consider this entire foundation system to be comprised of two masses. So one is this mass. So on top of this spring, we have this mass. Okay, so this is the absorbing layer. Right, maybe there is an elastic pad or something like that. So, or maybe there is some system. So it is the absorbing layer. Then at the bottom we have the foundation. Okay, so this is the entire mass of the foundation. And this is the soil. This is the soil. Okay, so this spring is this absorbing material. So now if you look into this part here, so we have a hammer at top. So it falls down and it imparts a velocity, basically, we can see. It imparts a velocity to the mass m2. And the mass m2 gets compressed. So as soon as it gets compressed, so that compression will then put a force on the mass m1. It will put a force here, and then there will be vibration generated in the mass. So ultimately there is a force given, alright, and then there is a vibration of the natural vibration of the system, okay, and it dies out. Of course there is damping, but we are not considering that for the moment. Okay, so if you note this, so we have two masses and each has its motion in the z direction. So this is z1, z2. Okay, so this is z2 and this is z1. So two motions. So 2 degree of freedom system. Okay, so now how to analyze that? So first of all, let us consider only the top mass. Alright, so we know that this is a 2 degree of freedom system. So it is a 2 degree of freedom system. So why 2 degree? Because we will get two equations. We will see that. Alright, how? Now let us consider the top mass. Okay, so if the motion is z1, so if we differentiate that dz1 by dt, we will get the velocity v1, and if we again differentiate that dv1 by dt, we will get the acceleration a1, which is equal to z1 double dot, we can see. So first of all, we have the inertial force. We can write az1 double dot, that is the initial acceleration. Then what are the forces? Okay, so that will be m2, that is m2, and this will be z2, sorry, so this is z2. Okay, top mass is z2, This is M2, M2, and this is M1. This is K1 and this is K2. So we have the inertial acceleration in the mass M into acceleration mz2. Now, what are the forces acting on that? Now, if this mass moves a distance z2 and simultaneously this mass moves a distance z1. So, what is the compression in the spring K2? So, that will be z2 minus z1. So, if the mass moves z2 and there is a spring here, so the mass m1 moves z1, okay, and the mass m2 moves z2. So this is z2 and this is z1. So the spring will get compressed z2 minus z1. Okay, so the spring force on the mass will be k2 into the compression, which is z2 minus z1 is equal to 0. So I hope this you have, I mean, this has sunk in, you got this, okay. So here if you note, so if you note here, if the mass moves down, if now the mass is at this position like this, so it has moved down from here to here, which is z2, and similarly this end of the mass, this mass also has moved down, which is z1. So the spring as a whole will move z1 amount. Okay, and the compression will be, total compression in the spring will be the z2 minus z1. Okay, so that will be the compression in the spring, z2 minus z1. Okay, whatever displacement it is z1, so that minus z2, sorry, z2 minus that one, so that will be the compression in the spring. Okay, so we have the equation of motion for the top mass, that is, so that is one degree of freedom. So this is for the first mass, top mass. Now what about the second mass? Now obviously when this will move down z1, so we have m1 z1 in acceleration. Okay, m1 m1 into acceleration, so that is the inertial force in this mass, that is the first one. Then we have, there is a compression of k1 into z1, so z1 is a compression in the spring k1, the spring k1, it is compressed by this amount z1, which is z1, so the spring will give an upward force which is k1 into z1, so that is k1 into z1, so that is one force. Now apart from that, if here upward force is k2, in this spring the upward force is k2 z2 minus z1, then there will be an opposite force on the bottom mass by the spring. Okay, so that will be minus K2 Z2 minus Z1. So this spring is giving an upward force to the mass M2, which is given by K2 into Z2 minus Z1. So that is the upward force. Now if this is the upward force, the downward force it is giving on the mass of M1. So that will be minus of this one. So it is in the negative direction, opposite direction. So it will be minus of this one. So minus K2 into Z2 minus Z1. So we can reverse it and put the negative sign inside. So ultimately we can write K2, it will be Z1 minus Z2 is equal to 0. Okay, so I hope this, at least this part, it has you have understood. So now if you look into the system, so we have one mass which is vibrating at omega n1, we can say. So this is the vibration of the mass omega n1. And similarly, we have the vibration here, so omega n2. Okay. So yeah, reciprocating machines can also be sometimes isolated in that way. Okay, so just like this, we can give a spring and we can isolate the vibration here to the foundation. Okay, so that is also similar concept to this one. So we have 2 degrees of freedom. So this is the mass rotating up and down here over the spring, and we have the foundation here on top of the soil. Okay, so 2 degrees of freedom. So same thing. So we have now 2 equations of motion. So we have first of the mass m2, we can write m2 into z acceleration, that is z2 acceleration, plus k2 into z2 minus z1 is equal to 0. And for the bottom mass, we have m1 into z1 acceleration plus k1 into z1, which is compression in the spring k1. Okay, so k1 into z1 plus opposite of this force. If this is the force in the upward direction, this k2 z2 minus z1, then in the downward direction we will have k2 z1 minus z2 is equal to 0. Now the standard solution for this system is, or the generalized solution for this system is, we can write it in this way. So we have z1 is equal to, so we can write it a1 sine of omega n1. Okay, remember that omega n1 t. Why I am writing omega n1, it will be clear afterwards. Omega n1 plus a2 cos of omega n, again 1. Okay, so again 1 into t. So this is the motion of the top mass, or sorry, of the bottom mass. Okay, and this will be plus, we will have, so b1, we can write b1 sine of omega n2 now plus b2 cos of omega n to t. Okay, so the motion z1 will be influenced by the frequency of the top mass as well as the frequency of the bottom mass. So we have the frequency of the top mass and the frequency of the bottom mass. Actually, basically there will be two frequencies at which the system will operate. Okay, so this is the motion of the Z1. Alright, so there's Z1 motion, total combined Z1. Now similarly Z2 will be given by, now when there is a motion in Z1 here, so Z2 will be given by, so there will be an influence factor, or we can say a correlation factor between the amplitudes of motion between M2 and M1. Okay, so there will be an correlation of factors. So we can say A1, A1. So that is this one. Okay. So again the rest will remain same. So sine of omega n1t plus again A2. No, sorry, that will be A1. Okay, so A1 will be for this motion, that is correlating Z2 to Z1. For the omega n1 frequency. Okay, for that frequency, that is, and A2 cos omega n1 into t. So this is again one part of the motion. Then the remaining part we will have another correlation. So we can say that to be suppose A2. So A2 into B1 sine of omega n2 now plus A2 into B2 cos of omega n2 into t. So basically Z1 and Z2 both will be a summation of two different motions. One is this one, vibrating at a frequency of omega n1, and one will be this one, which will be vibrating at a frequency of omega n2. And obviously A1, A2, so the total amplitude of this frequency will be A equal to root over A1 square plus A2 square. So you can find it out. So this is sine omega cos sine theta plus cos theta. Okay. So it will be A1 square plus A2 square. A. Again similarly B will be equal to B1 square plus B2 square. So instead of writing this, we can straight away write Z1 is equal to so we can combine this A1 sine omega n 1t plus A2 cos omega n 1t, that will be one wave. Alright, so that we can say suppose C1 sine of omega n t, omega n1 obviously, okay, omega n1, and the rest we can say a d1 cos of, sorry, sine of d1 sine of omega n 2t. Okay, so here C1 will be equal to A, but obviously there will be, and we have to introduce, in that case we have to introduce one phase. Okay, so plus minus alpha in this case. Okay, if we directly equate this to this one. So thing is that we can represent that equation in different forms. So similarly, Z2 we can write, as D1, so if this is C2, so we can write C2, so we can write C2 sine of omega n 1, okay, again omega n 1 now in this case, plus D2, okay, so sine of omega n 2. So there are different ways. So basically here A1, what we have said here, so A1, so A1 is equal to C1 by C2, or we can say C2 by C1, so that will be easy. So A1 C1, yeah. And similarly A2 will be equal to D2 by D1. Okay, so that is a correlation factor here. Now thing is that we have to find out what is the natural frequency of the system. So what we will do is we will correlate this entire equation to one simple sinusoidal motion. Okay, we can do that because in next classes and the coming classes I will show you how we can do that when we will do the Fourier transform, and we will see how we can find out the amplitude spectrum and versus frequency. Okay, so that is a very interesting and very important analysis as far as earthquake analysis is considered. All right, so that we will do in the coming classes. So for now, what we will do is, so we will equate this. So we can say, so suppose here we can say A1 sine omega n1 t plus A2 cos omega n2 t, n1 t, sorry, n1 t, okay, plus B1 sine omega n2 plus B2 cos omega nt2 and T2 T. So this is Z1 is equal to this. So we can equate this to, as we have seen here, so we can write it C1 sine of omega n1 t plus D1 sine of omega n 2. Okay, so we can write that. Another way we can write is, we can write it to be A, suppose, sine of omega n t. Now this is a particular solution. So here omega n has two values basically. Okay, similarly A has two values. So we say A has two values and omega n has two values. So this is a particular solution. So we take a part of the solution. It is not the entire solution. Okay, so we can equate that. Similarly, we can also write sigma z2. Z2 is equal to, we can write B sine of omega n t. Okay, now at the maximum this displacement, suppose at the maximum displacement, so we know that the acceleration is omega m square. So in this case it will be a. Okay, so a is the amplitude, so omega n square a. Similarly in this case it will be omega n square b. So z1 acceleration will be this one. Okay, and z2 acceleration will be this one. Okay, maximum acceleration, that is. So putting that in this equation, that is, so what we will do, so we have mz1 dot plus k1 z1 plus we have k2 z1 minus z2 is equal to 0. So if we put that here, so obviously this will become minus m1. Okay, this will be m1 omega n square into a. So we put it here. Okay, and what about this one? So this will be become plus k1 into a plus we have k2 into a minus b. So we are assuming that both the masses are at their extreme position. Okay, and both the masses are vibrating with the same frequency. Okay, so we have this equation of motion. So if we put that again in the other equation, in this equation, that is this one, so we will have, similarly we will have, so we have m2 z2 acceleration plus what we have, it will be k2 into, this will be z2 minus z1 equal to 0. So here it will be minus m2 omega n square b plus k2 into, this will be b minus. So if you simplify and solve, you will get b is equal to a is equal to 0. So this is not applicable. Okay. Apart from that, you will have the other solution, which is the coefficients will be equal to 0. Alright, the coefficients will be equal to 0. So we have k1 plus k2 minus m1 omega n square, that is 1. Okay, and minus k2, and we have here minus k2, and here we have k2 minus m2 omega n square. Okay, so the determinant of this is equal to 0. Okay, so ultimately thing is that if you simplify that, you will get that. Alright, so it is not a big deal. Okay, so here what we can do, if we simplify this, so we will have, so this into this, we will have k1 plus k2 minus m1 omega n square into k2 minus m2 omega n square is equal to k2 square we will have. Okay, and here if you put three terms, now here we can define two very important parameters. So one is the circular frequency of the anvil. Okay, so of this mass m2. Okay, of the anvil, that is. So here if you see, this is the anvil m2. Okay, so we can define the angular acceleration of that. So that will be omega n. So what we will write here is, so since we will have two roots, so here omega n will have, we will have omega n1 and omega n2. Okay, so here we will define this as the natural frequency of this system alone. Alright, so we will write it as a, omega n a, root over k2 by m2. Okay, apart from that, we can define one limiting frequency term where there is no vibration, independent vibration of the mass m2. So the mass m2 is moving in sync with the mass m1. Alright, so it is this entire mass m1 plus m2, it is acting as a single mass and it is moving up and down. Alright, so the both the motion are in absolute phase. So basically absolute phase means there is no relative displacement. Alright, so it should not be absolute phase. We should not say that it is in no relative motion. There is no relative motion between m2 and m1. Alright, so the spring K2, it is not moving at all. It is not getting compressed or extended at all. So the entire mass m1 plus m2, it is moving up and down as a single mass. So that is the limiting frequency. Okay, so that limiting frequency, it is defined as omega n L is equal to root over. So definitely K1 is the stiffness here and the mass is m1 plus m2. And apart from that, we define one another term. So m2 by m1. Okay, so that is the ratio. So ultimately putting it in the equation, we will have, so if we put it here, so ultimately and simplify, we will have omega n 4 minus 1 plus, then we will have omega n there is no space here, so wait. Okay. So ultimately, if you just simplify this and put these values here, so what you will get is, just if you remember yesterday's class, so we got quadratic equation. So omega n 4 to the power 4 minus 1 plus theta. All right. So here it will be omega n a square plus omega n l square into omega n square. Okay, plus 1 minus 1 plus mu here, sorry, eta. Okay, and here it will be omega n L square into omega n A square is equal to 0. So this is constant C, this is constant B, and omega n square you can write it as x. So here it is ultimately x square minus bx plus c is equal to 0. Okay, so again a quadratic equation. So you can solve that and you can obtain omega n1 and omega n2. Just what we solved in the previous class, we have solved that. Okay, so look into that. So similarly, you can obtain the maximum amplitude. Okay, so amplitude you can obtain. So we will also see at a numerical ways of obtaining the amplitudes. Okay, so ultimately you can obtain the amplitude. So to obtain the amplitude, what you can do is at t equal to 0. Okay, so at t equal to 0, so suppose if I consider z1 is equal to c1 sine of omega n1 t plus c2 sine of omega n2t, okay, and z2 is equal to d1 sine of omega n, sorry, it will be c1 and this will be d1. Okay, so this is what we have written. So this will be c2 sine of omega n1 t plus d2 sine of omega n2 t. So if you place the initial condition here, so at t equal to 0, so obviously z1 is equal to z2 is equal to 0. Okay, now at t equal to 0, the velocity, this mass is also, it is, I mean, resting, it is not moving, so the velocity v1 is equal to 0. But what about the mass m2? So at mass m2, what will happen is that this hammer, it will fall and it will impart a velocity of v, suppose we can write v naught. Okay, so v1 is equal to v naught at that time. So this is a parameter v naught. So v naught, which is the velocity which the hammer imparts on the anvil. Okay, so that is a machine property, and mostly that parameter has to be supplied by the machine manufacturer. All right, but there are other ways also we can obtain that, so we will look into that. So ultimately, if you put this condition in this equation and in the above equation, all right, so here ultimately using omega 1 and n1 and omega n2, so we will have the maximum amplitude of m1, which we can say, suppose capital Z1. So that will be given by omega n a square minus omega n L square. Okay, So that is already you have obtained. Apart from that, we have omega n a square minus omega n 1 square. Sorry, this will be n2. Okay, so n2 square, and divided by, we have omega n a square into omega n 1 square minus omega n 2 square, right, into the v naught. Okay, so this is the maximum amplitude. So if you consider this z1, so we can say the function, this function z1, that is z1, we can write it as z1 into sine of omega n1 t by omega n1 minus sine of omega n t2 by omega n2. Okay, so we have two frequencies again. So total vibration of the mass m1, alright, displacement function of the mass m1, it is given by, it is actually governed by two frequencies. Okay, one which is at a frequency of omega n1 and one which is at a frequency of omega n2. So if we have this omega n1, okay, and we have omega n2, so the function of z will be a summation of these two. But we will see how we sum that up. In Excel, we will plot and we will see it thoroughly. All right, one by one we will see to make it very clear. So similarly, Z2 will also be, we can obtain. Okay, so Z2 also we can obtain, and that part I'll leave it to you. You can see that. Okay, just simple mathematical calculation. All right, and you can look into that. That is not very tough. But thing is that if you see into that and correlate the two, then it will be easier. Now apart from that, what we have to find out is the stress in the pad, right? So pad means, so here K2, so it is a elastic pad, if you remember, right? So we consider that as a pad, right? So here it is, there is a elastic pad. So the permissible stresses in this pad, it should not exceed the limit which it can take. Okay, so to find that out, what we have is the stress in the pad is K2, which is the stiffness, into Z1 plus Z2, which is the total displacement, plus Z2, and divided by the area of the pad, we can say A2. Alright, so here if this is the pad here, okay, so sigma 2 on the plate, on the pad here, so we will have K2 into Z1 plus Z2 by area of the plate. Okay, so we can say, so M2, since it is M2, so we can say area of the plate is of the pad is A2. So that is the 2 degrees of freedom analysis. Okay, so we have seen how we can use different equations to represent the same motion, and we can use that to our maximum benefit, and we can find out what is the frequency of motion, and as well as we can find out what is the amplitude. Okay, in fact we will also see some other ways and more easily understood ways to analyze the same. All right, so in the coming classes. So apart from that, obviously, whatever the discussion we did regarding the reciprocating machines, we need here also. So regarding machines, we need the weight of the machine, mass of the machine, that is. All right. Then the hammer. What is the frequency of the hammer? What is the efficiency of the hammer? All right. Then we need what is the velocity with which the hammer will hit. Okay. So and the energy that it will impart, so that should be known. So that should be known. So apart from that, subsoil conditions we have already discussed. So in the reciprocating machine, whatever it is required, here also you require the same properties, so let's same data. Apart from that, we have the vibration criteria. So definitely the amplitude, permissible amplitude has to be there. So regarding, there is a IS code, this given, standards given, some thumb rule. So correlating that with the weight of the hammer, weight of the hammer or top, whatever you say, all right, or the hammer. So if the weight of the hammer is 1 ton, then the amplitude, maximum permissible amplitude is 1 mm only, 1 mm, right? So low, you can see 1 mm only. So if it is 3 ton, it goes up to 3 to 4 mm. All right, in between, if it is 2 ton, it is 2 mm. And for the foundation block, all right, this is for the anvil. And for the foundation block, it should not exceed 1.2 mm, the amplitude. All right, Z1 should not exceed 1.2 mm. So this is Z2. So permissible stresses, as we have discussed, so there are, it should not exceed that much. All right, so the concrete, wood, and steel, whatever are used, so that has to be within limits. Now here, as we have discussed, so of course natural frequencies we have already obtained. So we have the anvil, natural frequency of the anvil. We have the natural frequency of the limiting natural frequency of the entire system. Then we have omega n1 and omega n2. Okay, so these are the four frequencies which are of importance. So then we have the mass ratio m2 by m1. Okay, so this has to be found out. Then we have the amplitude of motion. So we just now found out z1 is equal to, so we have omega n a square minus omega n l square. Easy to remember, all right? So into omega n a square minus omega n 2 square, all right? So then we have omega n a square into omega n1 square minus omega n2 square. So into the velocity of the drop. So this is the maximum amplitude of the anvil. Okay, similarly you will have the maximum amplitude of the this foundation also. Now velocity of dropping parts to the anvil. So that is very important. Okay, so one way to obtain is if you know the height of the fall. So if the height of the fall is known, so suppose this is the hammer and this is the anvil. So you know this height. Okay, so definitely this is the potential energy is root 2 GH. right, and the velocity is given by, there is an efficiency, all right, so we have to, what is the efficiency of the hammer? So if it is 100%, definitely v velocity of the fall of the hammer, so velocity of the hammer is equal to root 2 gh, and if it is not, so we have a this efficiency of drop. Okay, efficiency of the drop, so this is defined as that. In some cases what happens, there is a pressure given, so it is pushed down. Alright, instead of letting it fall freely, it is pushed down. So in that case you have to consider that as well. Okay, so in that case you have to consider that as well. So in that case what it will happen is, we will have, so root over twice g w naught plus p into a into c. Okay, so this is a into c is the area of the cylinder, sorry, AC, that is AC, not A into C, this will be AC. Okay, so this will be AC, P into AC, area of the cylinder, so that is force, so that is force, P pressure into area, so that is force. Okay, so all into H divided by the weight of the hammer, that is this one, weight of the hammer, this one. Alright, and then of course the efficiency of the fall, whatever is the efficiency of the fall, 100%, 80%, 60%. Okay, so generally efficiency is taken as around 65%. Thumb rule. Okay, thumb rule. So thing is that when the hammer falls, generally there is a reduction in the velocity. All right, so this is the velocity of the falling hammer. So when it falls, so due to the absorbing, properties of the elastic pad, some amount of energy is absorbed by the pad itself. All right, so we introduce a coefficient of restitution there. All right, so that is a coefficient of elastic restitution. So VA, we have VA, that is which we will use to calculate the maximum amplitude of motion, that is VA. Okay, so that we will have as 1 plus E by 1 plus W2, where W2 is the weight of the anvil, okay, by W naught, which is the weight of the hammer, and into this velocity of the fall, that is VH. Okay, so that is the velocity of the fall. So that is what we have to obtain. So E also it is given. So E, the thumb rule to take E, we can take it as 0.6. Okay, so when the hammer falls, so it hits the anvil. As soon as it hits the anvil, some amount of energy, it gets dissipated quickly in the elastic pad. So that is the elastic restitution. Then it generates the velocity, which moves on to the foundation, and then the foundation and the anvil, it starts to move, and there is a harmonic motion. So it is like this, and there is like this. Okay, so some amount of energy is absorbed by this elastic pad. So that is taken care of by introducing this coefficient of elastic restitution. Okay, So the velocity, to find out the amplitude, you will use this VA, not this VH, the fall of the hammer. Okay, so this sums up our machine foundation. Okay, this sums up our machine foundation, and in the next class we are going to continue with a very interesting and most crucial chapter of this course, that is the earthquake design parameters. Okay, so earthquake design parameters, so that is a very interesting and very important part of this course, and we will see it, and it has a lot of researches going on, lot of things are updated, all right, so it is very interesting. So we will stop here today.